Today we're going to understand the theory behind the simplex method. There are many videos online that explain how to do the simplex method, but not too many that explain, how it really works. All right, so let's look at an example. Maximize z equals 3x1 plus 5x2 so that x1 is less than or equal to 4, 2x2 is less than or equal to 12, 3x1 plus 2x2 is less than or equal to 18. x1, x2 greater than or equal to 0. All right, so let's first draw this feasible region and look at the picture. Now, the simplex method doesn't need a picture at all to solve linear programs, but if you want to understand how the simplex method works, it's good to see a picture. All right, so let's see. So 9 down to 6. So there's 9, 6. So we have one boundary, one constraint boundary. Then we have x2 is 6. And x1 is 4. Okay, so we have our feasible region here. The feasible region would of course be this region here. And let's emphasize the feasible region. We have a corner here, corner here, corner here, corner here, and a corner here. Now, we know that the optimal solution to every linear program must occur at a corner. So you might say, why do we need any simplex method at all? Why don't we just check all of the corners? The trouble is if you have a huge amount of variables. So let's say you have a linear program with many, many variables. How many possible corners could there be? Well, if this is an aside here, so if we have 5 constraints and 3 variables, then we would have, then the total number of basic corners we would have is something close to 8 choose 3, which is equal to 8 times 7 times 6 divided by 3 factorial. Now, what happens if we have 100 inequalities, which are the same as constraints, and 200 variables? Well, in that case, if you want to know how many corners you could possibly have, it's a stupendously large number. 300 choose 100. Actually, change this to a 300 here. 100 equations, 300 variables, 300 choose 100. How big is that number? That number is basically 4 times 10 to the 81st power. And if you had a computer that could check each corner in a millionth of a second, it would take 4 times 10 to the 75th seconds to find them all. How long is that? Basically, if you say the age of the universe is 20 billion years, it's 2 times 10 to the 10th ages of the universe. No, sorry. 10 to the 58 ages of the universe. In other words, the age of a universe is absurdly long, 20 billion years. You would have to repeat 20 billion years, an even more absurdly large number, 10 to the 58 times. In other words, that might as well be infinity. That number is so large. So what I'm saying is, as the dimension of the problem grows, the number of corners goes to infinity. It goes really fast. And real life problems can have many, many variables. So thankfully we have an algorithm called the Simplex Algorithm, which will solve this in a few seconds often. Pretty amazing. Okay, so how does the Simplex method work? Why does it work? All right, so first thing, just to get a brief idea, we start at a corner. And we use the objective to say which way should we go. Well, better to increase x2 than it is to increase x1. You'll get a 5-fold increase rather than a 3-fold increase. So the Simplex algorithm will tell us move up. Then eventually we're going to hit a brick wall. This brick wall is this constraint right here. So algebraically we're going to figure out we hit a wall. And we're at a new corner. Then what we're going to do is we're going to twist the picture. It's called pivot. We're going to measure from this point of view. See, and we were at the point 0, 0, right? This is x1 equals 0, x2 equals 0. It was rather easy to say how to efficiently increase z, increase x2. But when we're here, at this point, it's not so easy to see where to go next. If we were in higher dimensions, there could be many, many different corners to go to from here. So what we'll have to do is algebraically change our point of view so we can see the gradient of z more easily along the various edges. So we're going to do some algebra, and then we'll be able to say, is it better to move to this edge, maybe along this edge, back to that corner, or should we go back? Usually that's not going to be the case, but if this was in higher dimensions, there could be another edge to follow through. Okay, so let's say we finally get to an edge, a corner, and let's say we look at our corner and we look at the neighbors. So imagine you're in 3 dimensions. I'll draw a little picture in a second. So let's say we're in 3 dimensions here. So this would be a higher dimensional simplex. Let's say we're at the point P, and we're considering whether or not we should go to each of these corners, A, B, or C. All right, so the simplex algorithm took us to corner P. And we have to decide, maybe we went along this edge right here. And we have to decide which way should we go now. Should we go here to A, to B, or to C? You know, back to D. Maybe you could even think about that. All right, so here is the rather amazing fact. This is called the optimality test. So suppose P is more optimal than A, C, B, and D. Those are its immediate neighbors. Those are its adjacent vertices. So P is adjacent to A, B, C, and D. Now imagine there's thousands and thousands of more corners in this higher dimensional feasible region. The surprising fact is this. So if P is better, more optimal than all of its neighbors, then it's globally optimal. It's the optimal solution in the entire problem, even if there are millions and billions of corners far away from P and not directly adjacent. So if P is better than all of its neighbors, it's better than all corners. So let's say you have a classroom and one person is taller than everybody in the classroom. Then according to this theorem, if this were true in that case, that person would be taller than everybody in the world. So it's not true, of course, in real life, but in the geometry of linear maps and hyperplanes and simplicial regions like this, it is true. So that's how we know when we find the optimal solution. If it turns out that this corner is better than that corner and that corner, it's better than all the corners. You don't even have to test that corner, or anything. So it's really a lifesaver to tell us when we have the optimal solution. All right, so let's see how the simplex does some of its algebra. All right, so the first step is to augment. So augmenting means we're going to take away the less than or equal to's and add a slack variable. So I'm going to add an S1 here and change this to an equal sign. I'm going to add an S2. Let me rewrite it right below. Let me rewrite it below so it's a little more clear. So first thing is move everything to the left side. So remember, we're maximizing z. So we have z minus 3x1 minus 5x2 is equal to 0. Okay, save, put a little space for the 0 here because we have to add a few more variables. Okay, so x1. Now instead of saying equals 4, make up the difference with what's called a slack variable. And this S1 will hold the difference between 4 and x1. So if x1 is equal to 4, S1 is 0. If x1 were 3, then S1 would be 1. Right? It's the slack. It's defined to be 4 minus x1. That's S1. Okay, what's the slack in that equation? So 2x2 plus s2 is equal to 12. So s2 holds the slack between 12 and 2x2. And finally, 3x1 plus 2x2 plus s3, you need a different slack variable for each equation because they don't have to be the same number, 18. Now we have 5 variables. It looks like we've made things worse, harder. And they all must be non-negative. Okay, so are things better? Well, we have more variables than we did here, but now we have all equal signs. And it's much easier to manipulate equations with equal signs than it is with inequalities, because this is a bit ambiguous. It's hard to solve equations with inequalities. So we store the ambiguity in this slack variable. Okay, so how do the slack variables work? Well, take any 2 variables out of 5 and you will get a corner, or at least an intersection of 2 constraints. So let's take a look at this. So let's say we let x1 equals 0 and x2 equal to 0. Set 2 variables equal to 0. Well, we get this corner right here. So let's call that A. That's A right there. Okay, let's let x1 equals 0 and s2 equal to 0. All right, so when s2 is 0, x2 is equal to 6. When x1 is 0, x1, you're on this line right here. You're on that the x2 axis. So we're at this corner right here. So that's B. Let's try setting S1 equal to 0 and S2 equal to 0. So S1 equals 0, S2 equals 0. So if S1 is 0 and S2 is 0, X1 is 4, X2 is 6. We're right here. And this is the point 4, 6. Now notice it's outside of the feasible region. So let's say we continue, and once we know 2 values of 2 variables, we can solve for the rest of the 5 variables. Let's do that. So S1 is 0, S2 is 0. We already solved. X1 is equal to 4, X2 is equal to 6. One more to solve for. So let's solve for S3. So 3 times 4 is 12. 2 times 6 is 12. 24. 18 minus 24. S3 is negative 6. Oh, that's a problem, because all the variables must be non-negative, but S3 is negative. That means you're sort of 6 units outside of that constraint. You violated the constraint by 6 units, right? S3 is negative 6. You exceeded this 18 by 6. So this is a great way to know whether you're inside the feasible region or not. If you're in the feasible region, all of the variables will be greater than or equal to 0. But as soon as you leave the feasible region, a variable will turn negative. And that's the great algebraic way to see that you're inside the feasible region or not. So when we want to check whether or not we're leaving the feasible region, then all we have to do is verify when we're when one of the variables turns negative. Okay, so let me erase this, since we now understand how these slack variables work. Setting two variables to 0 gives you a vertex, and these are what are going to be called the non-basic variables. Choosing two variables to be 0 means you've chosen two non-basic variables. So let's start the simplex method. Just try to do one iteration with the picture and keeping all the variables in. All right, so first step is we're going to start at this corner here. The number of non-basic variables is equal to the number of variables, which is 5, minus the number of constraints, which is 3. So 5 minus 3 equals 2. So we have two non-basic variables. In this form, we're in standard form, which means 0, 0, 0 is a solution. In this case, it's a 0, 0. We always start with this when we're in standard form. And any problem can be put into standard form. This is standard form, a maximization problem where 0, 0 is a solution. It's a little bit more technical, but that's the basic idea. Okay, so the number of non-basic variables will be 2. The number of basic variables is equal to the number of constraints. So it's equal to 3. All right, so we start out with x1, x2 as non-basic. So non-basic, x1, x2, think of them as being set to 0. And the basic are S1, S2, S3. Okay, so what we do is we look at our objective and we say, which variable should we increase? You can only move along edges in the simplex method. You're not allowed to move along the interior. You always stay along edges of the feasible region. So if we increase x2, z will get bigger 5-fold. If we increase x1, z will get bigger 3-fold. More efficient to go with the 5. So the simplex method says take the most negative number in the objective. So we're going to increase x2. So we'll say x2 is going to enter the basis next step. It'll increase. And we have to figure out which one of these basic variables is going to turn to 0 when we cross our first boundary. So that's the ratio test. So let's see. So let me erase this here. Okay, so we're increasing x2 and we're keeping x1 fixed at 0. That means we're moving a one-dimensional line along an edge. Okay, so let's set x1 equal to 0 and let x2 be free in the constraints. We're done with the objective for now. So when x1 is 0, let's see what we get. So 0, so S1 is equal to 4. 2x2 plus S2 is equal to 12. x1 is 0, so we have 2x2 plus S3 is equal to 18. Now the question is, we want to make x2 as big as possible, because the bigger we make x2, the bigger z will be. We want to go up to infinity if we could, but we're going to hit a brick wall, and we know where the answer is right there. So you look at your equations. Here, x2 can go to plus infinity, right? There's no problem S1 does not depend on x2. So it does not stop x2 from increasing. But here, when x2 is equal to 6, s2 would be 0. So x2 must be less than or equal to 6. Or let's just say x2 is equal to 6. When it's equal to 6, then s2 is 0. And when x2 is equal to 9, s3 turns to 0. Notice this is called the ratio test. We just took 12 over 2 and we got 6. 18 over 2, we got 9. So we can't let x get to 9. That's too big because we left the feasible region right here at 6. So this is the relevant information. When x2 reaches 6, s2 must drop to 0, right? 2 times 6 is 12. 12, there's no slack. As soon as you pass 6, s2 will become negative. So what that means is that s2 will become a non-basic variable, and x2 will leave the basis. So let's write that down. So we're going to interchange s2 and x2. So we'll put the s2 here, s2, and put the x2 here, and I'm sorry, right here. It's the s2 and x1 and s1, x2, s3. All right, so we have one key step to do, and this is the hardest step. So we've now moved to here. So right here, we know that x1 is 0, s2 is 0, right? Those are our non-basic variables. So we're right here. So the key step is to decide where to go next. But in order to decide where to go next, we need to rewrite z as a linear function of the non-basic variables, s2, x1. We have to play around with our variables and get rid of the x2 right here and replace it by s2. In other words, and this is where the algebra comes in. And I'm going to stop in a moment because it's better to do that in the tableau method, but I'll try to explain a little bit of the theory. Okay, so what you have to do, this is the key equation. See, x2 and s2 traded places here. You want to make x2 a basic variable. So you see how the basic variables are all alone in their column? They're in row echelon form. There's zeros above them, and their 1 is the coefficient. So you want to do the same thing for the x2s. What you're going to do is divide this equation by 2. So and then you want to multiply this equation by 5 and add it to that equation to zero out the x2 there. And then you want to use that x2 to zero out that. And the result is that an s2 will pop up here with some number, and this one will be gone. That'll be a 0. And then you could say exactly z as a function of x1 and s2. And you could tell which way to go to increase z most efficiently. And then you continue and continue. And you stop when the objective tells you that it doesn't pay to go to any of the neighbors along any of the edges because it'll just get worse. And that's how you know that you're at the optimal solution. So just to see what it would look like. So let's see, I divided by 2. So this is a 1/2 here, and that's a 6. This was a 18, right? Okay. So what we would do is we would say -5 times this row plus, no, 5 times, so let's call this one, this is row 0, row 1, row 2, row 3. We're going to say 5 times row 2 plus row 0, put the answer in row 0. So 5 times x2 plus this x2 would be 0. So that'll become a 0 there. It'll just go away. 5/2 plus 0 is 5/2 s2. 5 times 6 is 30. All right, so what that means is z is 30 right here. See, if you let x1 equal to 0 and s2 equal to 0, z is 30. And now you could clearly see that if you increase x1, z will get better threefold. So that the next step will be to go this way until you reach that corner. And when we get to that corner, we'll see that we're at the optimal solution. All right, so that's the theory of the simplex method. When there's no negatives, that means we're better than every one of our neighbors. And then the algorithm terminates.